Welcome all of you to our IMSE webinar today. My name is Tuomas Heikkilä and I'm hosting this Designing IMSE Electronics webinar together with Sten Iversen from Altium.
Hello everybody.
Our presentation duration today is approximately 40 to 45 minutes, and after that we will have some time for your questions. You can send questions anytime via the chat, but we will see them in the Q&A session, which is the next part of this webinar. And of course, recording of this session and slide material are shared later on. And one practical thing, so there is no exit button in this webinar UI on PC, so closing the browser will exit the webinar. And then short introduction about the speakers. I am Tuomas, Principal Electronics Engineer. I have worked for TactoTek approximately 8 years, and all of this time, more or less, worked on IMSE Electronics design. And then we have Sten. So Sten, could you introduce yourself?
Yes, hello, I'm Sten Iversen. I work as a field application engineer for Altium. I just recently joined Altium like a year ago, but I have been working with Altium since it was called summer '09. Before that, I was also doing developing for Iversen Denmark. So I was part of their R&D developing, and we were, designing fibers and digital subscriber lines also. So that's basically me.
Okay, thank you. And contents of today's presentation you can see here. So actually we have two parts. The first part, designing IMSE Electronics. I will present this one, and after that I will change control to Sten, and Sten will show Altium Designer more in details and how we can utilize it in IMSE Electronics design. So, designing IMSE Electronics, and if we think about what is the electronics in IMSE products, the first thing, of course, we can see that it's a bit different than what we have used to see in traditional products, which contains traditional PCB electronics. And you will see the main differences in best way if we go through those examples what we have here. So the first one, I put the pointer. So the first one you can see here, this is door lock, and we implemented this front cover, black front cover by IMSC technology. This front cover contains illuminated icon and capacity sensor. And by IMSC, we were able to bring the capacity sensor close to the touch surface, and by that way, we were able to improve the capacity sensor sensitivity. Then the second example product, this is quite typical IMSC product as it contains 3D shape. So in this case, we implemented capacity slider around this vertical surface. We have illumination indicating the finger position in the slider, and in addition we have capacity sensors with illuminated icons here. So as I said, this is quite typical in IMSC products, and this because this is 3D formed product, and it at the same time it means that the electronics what we have inside this part needs to be in 3D form. So in IMSC it is very typical that electronic circuits needs to get 3D form. Then the third example, ashtray cover. Typically this dummy part does not contain electronics, but with IMSC we were able to bring electronics products like this. So actually the mechanical dimensions were same that without electronics or with electronics. So with IMSC, we could bring electronics new places. We can bring electronics in products which have 3D shape, and also when electronics needs to get 3D shape. So this is the key thing for IMSC products, and of course this sets certain requirements how the electronics should be in those products. If we go more in details how IMSC structure is, so we can see that it contains many different disciplines like mechanics design, illumination design, electronics design. Of course, there is industrial design and so on. In addition to this, it contains many different parts like mechanics, electrical components, electrical circuits. So there are a lot of different parts, different disciplines, but the key point is that we integrate all of those in one single unit. So basically, IMSC products requires same technology areas that any other products, but we integrate all of those in one single piece. From electronics design point of view, this means that electronics design it is just one part of whole product, and we cannot design it as an all and just integrate everything in the latest manufacturing phase. It doesn't go that way, but instead we have to design mechanics, illumination, electronics, and all other disciplines at the same time, parallel, and we have to take into other technologies and their requirements. And electrical engineer, when he or she is designing electronics for IMSC products, needs to get understanding how is the path from concept to final product. So at beginning we have concept, we have requirement specification, and from those we should be able to convert the electronics design so that we have all required functionalities, capacity sensors, illuminations, so on. And of course, we need to design layouts such that the electrical performance requirements are fulfilled. This is not enough, but in addition, electrical engineer needs to understand how the layout is manufactured in printed electronics with components. So this printing, surface mounting, those sets certain criteria how the layout should be. And of course, electrical engineer needs to understand how the final product is manufactured. So in IMSC, we have thermoforming, which makes this electrical layout in 3D form, and the latest manufacturing phase is injection molding, where we put plastics on top of our component. So by injection molding, we are encapsulating our electrical circuits and components within the plastic. And of course, those manufacturing phases have impact how the layout should be, that we can do those manufacturing phases. And how we do all of those, how we take all of those into account in electronics design. So basically, IMSC electronics design, we have recognized there is 3 critical elements. Those are materials, manufacturing, and stack, material stack. Basically, those same key elements are valid also for PCB design, but the differences comes the details what we have in each key element, as you will see. In material side, the main differences are substrate of the electronics. So we don't have FR4, but instead we have thin plastic film. In IMSC, traces are not solid copper, but instead we are using silver ink, which we printed by screen printing. If we need multi-layer layouts, we need to design dielectric on crossovers. So those are the main differences what comes to the material side. Materials are different, and this means that their electrical characteristics are different as well. In manufacturing side, we have different methods to do electronics. So as I said, traces are printed by screen printing method. Also others can be used. We use conductive inks, dielectric inks for creating the electronics. The 3D form of our electrical circuit will be get by thermoforming, and we do the injection molding for creating the mechanical structure of the product, and at the same time we are encapsulating electronics within the plastic. So because we have different manufacturing methods, it means that our design for manufacturing rules are different as well. And with different materials and different manufacturing methods, we will get different electrical stack up. So the stack up, this is not only electrical stack up, but in addition to this, it is mechanical structure of the IMSC product, and for example, optical light guide for LEDs, what we have inmolded within the plastics. So electrical stack up, it contains our P film, where we have electronic circuits, then the injection molded resin, and then the A film. And this stack up actually defines how is the electromagnetic field behaving within this structure. And to achieve the performance, what is required by our customer, it definitely means that we need to understand this whole full stack and must be able to simulate electrical behavior with, for example, with 3D electromagnetic simulator tools. In practice, it means that when we are designing layout like this, at first we need to find out what are our materials. So we are using conductive inks for traces, and for those inks we need to find out what is the square resistance of the printed traces. And then, because we have plastic films, injection molded resins, we need to find out what are dielectric constant and strength of those materials. In manufacturing side, trace dimensions are defined mainly by printing. So trace width, clearances, and design rules for those came from the printing methods. We need to design dielectric, so again, printing sets certain requirements how the dielectric design should be. And when we do the 3D shape by thermoforming for the layout, at the same time we are stretching our traces, so we need to think about, we need to analyze what happens to traces, and we have to design the layout based on requirements what comes from thermoforming. And same is applicable for injection molding. So we have to take injection molding into account, for example, by analyzing where is the injection molding gate, and design electronics around the gate properly. And then one thing for electrical engineer is related to stack, of course. So in the stack phase actually means the electrical simulations. So we have designed layout, we have material information, we have our material stack, and we need to combine those together. And after that, we can do the electrical simulations, and from there we get the basic electrical parameters which defines the performance of our electronics. So we are simulating resistances, capacitances, inductances, and impedances if those are needed. And typically some 3D electromagnetic simulation tool is needed for this design phase. And of course, one important design phase is integration design. So we need to design actually IMSC product together with other engineers. And one interesting design element is the thickness of the part. So mechanical engineer has own requirements how the thickness should be. Electrical engineers typically wants to minimize the thickness for achieving the best performance for capacity sensors, and then optical engineers wants to have certain thickness for having the best optical performance. And definitely because we have three engineers designing the same part of the product, so it means that we have to find out the best compromise for everything, that we can fulfill all requirements. And of course, this means that all engineers should understand his or her technology and its limitations and capabilities. And of course, IMSE Electronics design is tolerance design. And in IMSC products, when we are using conductive inks, the resistance of traces which are printed by conductive inks are typically significant. So we have to take it into account in all our electronics designs. And in addition to this, the tolerance of the resistance must be taken into account. So tolerances comes, of course, from the materials itself, but also how is also IMSC manufacturing has impact. How is the deviation of the resistance from the nominal? And this is very important and quite unique for IMSC, because if we compare trace resistances between conductive inks and pure coppers, we can see that there is huge difference in terms of nominal resistance, but how is the resistance tolerances. So resistance design is very important in IMSC products, and we need to design resistances with tolerances. So actually this slide concludes IMSC Electronics design. So the first thing is that make sure you understand electrical characteristics of the materials that you are going to use. The second one, make sure you understand what is design for manufacturing rules. Third one, it's recommended to make inductances, capacitances, resistances simulation with known electrical characteristics of materials and designed layout, and with proper material stack. And all of those we need to design with tolerances. And last but not least, you should make integration design together with other engineers. So basically those four items are the key points when we are designing electronics for IMSC products. And then a couple of words about the tools. So basically, electronics designs for IMSC products we are designed by Altium tool, and the main reason actually is that Altium supports IMSC electronics design quite well. So there is features where we can add IMSC electronics design rules, and Altium is able to check our design layout against those design rules. In addition to this, Altium and its printed electronics extension supports dielectric design, which helps IMSC electronics layout design a lot. And now why we are here today with Altium is because we have collaborated on creating this IMSC design automation functionalities for Altium Designer, and these features enables designers around the world to design IMSC products easily with Altium Designer. And I'm happy we have Sten from Altium here presenting this great tool and its nice features. So, Sten, stage is yours. So.
Okay, thank you for this wonderful presentation, Tuomas. I will try to keep up the good work then. Okay, can I take the screen?
Yep, I stop screen sharing. So, yeah.
Okay, and let me just start my presentation here. So, just 2 seconds. Here we go. So my agenda for today is, of course, to tell you how Altium can do this and actually show this live, how to make some of the IMS designs a little bit easier, actually. So the agenda is that I will do a short, very short presentation in this one here, and then I'll switch to a live demo in Altium 20, and of course also using our cloud product, which is called A365 here. So if we look at the technology and in terms of what the technology delivered, the game actually remains the same. Now, electronic components are connected together via conductive pathway, forming an electronic circuit that perform some kind of useful function. Now, what differs is the approach used to build up the circuit here. The traditional PCB uses a layer-oriented fabrication technology. This is a reductive process. So each conductive layer starts as a continuous sheet of conductive material, such as copper, for instance. This is then etched away, leaving only the copper that performs the required conductive pathway here. Now, it is also a multi-stage process, as the individual conductive layers are sandwiched together with alternating layers of isolation and various drills and post-plating process applied for vias and such. If we look at structural electronic, or in specific IMSE electronic here, this is an additive process. Now the signal pathways are printed directly onto some kind of substrate, normally a plastic film here. So if a subsequent signal pathway needs to cross an existing pathway, a small patch of isolation is printed directly in the required location, as you see here. I don't know if you see my cursor, but you can see the black spot here on the lower right corner here. And this will act like a tiny bridge, so that it will allow the signal path to cross each other here without connecting it. If we need a connection from, for instance, layer 1 to 2, we will place a via like normal. We do that like normal PCB also here. Yeah, okay. So in order to fully support the structural electronic, Altium Layer Stack Manager has a feature called Printed Electronic, and you can enable this in the feature pull-down menu here at the top. You see it there, and this will remove the core materials and allow you to work with the copper and isolation layers instead here. One of the key elements in designing the structural electronic is the tool's possibility to automatically detect shorts in the agent couple layer. So it will have to detect if you are creating a short from layer 1 to layer 2, and this is kind of difficult in ordinary tools, but we built this into Altium, so it's kind of makes it very simple for you to fix this one here. We will automatically detect shorts to it, and we will generate these isolation patterns, and we will see this in the live demonstration also here. Okay, let's switch to a live demonstration. I will start Altium here, and I can see you are seeing it. Now, currently I am connected to my cloud service here, or my workspace here. So I will create a new project in there. By doing so, I am also sharing the project with my entire team, so they can take over if I need some help with it, and so on and so forth. So let's actually try and create a new project here. Going for File, New Project, and I will put this one here in my cloud service or my workspace here. And let's call this one here IMSE test, and this is the webinar project here. You can also see that I will enable formal version control. So this allows multiple workers to work at the same project at the same time, and then we can merge designs like you do with version controls here. So I will create the project. It takes a few seconds, and then we are ready to go. Now I see that it's taking a little bit longer time than normally. I think this is because I am also using this webinar stuff here on my internet connection. But now the project has been created, and the first thing I would like to do here is to add a schematic. So I'll right click and say add new to project, and I will add a schematic. It will generate the schematic here, and in this case, I won't do any fancy stuff like adding templates from the managed template of my workspace, but just simply keep this one here. I will, however, place a couple of connectors, and I will take those connectors from my workspace library here. And this library is, of course, shared with my entire team. So let's have a look at components here. And as I recall, yeah, I can, of course, let's kill this search here. And I can, of course, scroll down and look for connectors and then find the right connectors in all of those here. You see, I have quite a lot of connectors available, but I recall that the connector is named something like SM06. So I'll just type it up here, and it will find any connectors that has some SM06 in some of the parameters. And this is the connector I want to use. So I'll simply right click and say place this one. It will then get attached to my cursor, and I can start placing it. So let's zoom in a little bit and placing it. Something like this. And for the connectivity, I will simply just attach it to each other here and then pull away. Then we have the connectivity like this. And I also need to give them designators. For that, I will use the tools automation here, saying, okay, let's annotate the schematic quietly. So I don't have to interfere with anything. It will just give it names 1, 2, 3, and 4. Now, this is basically the design, very simple, but it's okay to show you this functionality here. Let's save the sheet. Let's save this one. Let's call it connectors. Now, I, of course, also need a PCB, so we will add this to the project also. Right-clicking here, add new PCB. And For my default, it will generate a standard PCB for me, 2 layers with standard cores and everything here. So if you look at in 2D mode here, it will look something like this. If we switch to 3D mode, you can see that I have 2 layers and here some kind of thickness of the PCB also here. Let's quickly change that and actually enable the printed electronic. So in here, I will go to the layer stack manager for that. And in here, we will see the couple layers, the core and so on. And I will then enable the feature called printed electronics. It's a little bit slow today. So here we go. You can see I have the top overlay, I have the solder resist, I have my copper layer, I have the dielectrical FR4 core here, and so on and so forth. So let's enable the printed electronics here. By doing so, I will also kill or delete the core because it's not needed anymore. However, since this is going to be injected molded into some project, I will also remove the top overlay and the top solder here. So let's delete those layers here. Delete layers and delete these layers also. So now I'm basically down to 2 copper layers. I of course also need one of the isolation layers. So let's add a layer here by right-clicking, say let's insert a layer above, and this should be non-conductive. You will see here that it will choose automatically a material called NCI 001. If I don't want this one, I can click here to change it to another material. It will open up my material library here, and in here you can see that this one here is the standard one you get when you are installing Altium here, and I have added another one called TactoTek standard isolation with a thickness of 4 mil here. Let's use that one. Now let's have a look at the material library for it. So you can see here I have the printed electronic materials here. Now they are basically just 2 materials. I have conductive and non-conductive. So in here you can see for the conductive side I have added the TactoTek here, silver ink 2 mils. You can of course add your own. Just click new here. Let's click new. Give it a name. Test, for instance, and another, let's say that this is gold, and a thickness of 1 mil. Simply click update here, and then you have the options also to use that one also. You should then, of course, save this one somewhere where your team can also access this material library here that you just created. Now, let's just cancel this one here. No, I want to change it here. And for the copper here, oh, sorry, not copper, for the conductive stuff here, I will select the silver ink from TactoTek. Okay, so this is basically my stack up here. I have 2 conductive layers and 1 isolation layer. Let's switch back to the PCB and have a look. Now for the 2D presentation, there's no really differences. You can see the layers down here. I have layer 1, 3, and layer 2 then. But if we switch to the 3D mode, you'll see here nothing is actually shown because I don't have any overlay. I don't have any copper layers are in here, so there's really nothing to show right now. So basically we have nothing as it is right now. Let's save the PCB. Okay. And we will start to import the connectors or actually align the PCB with the schematic here. So for that, we'll go for design and import the changes here. Now the system will then compare the schematic with the PCB, and it finds that it needs to add a lot of these connectors here to the PCB, some nets that should be added also. It will also create a class for each schematic sheet that I have. So this will also be added, and it will also suggest me to add a placement room here. But for this case, I will leave this one out. Now let's import stuff. And now I have my connectors. Let's quickly place them here. And 3 up here and 4 down here. Now I will quickly do some aligning here. So let's just select these ones here and align them to the top. And this one, and align them to the left. And let's also move this one just slightly, something like this. So this is the circuitry that I want. And oops, not entirely. Let's move this one around like this, and I'll just make sure that they are aligned again, like this. And now for the routing of it, let's use the tool that Altium has, the multi-routing here. So let's select a lot of paths here and route them at one. So we will use the interactive multi-routing tool here, just selecting any of the connections like this one up here. And the tool will start routing here. Let's go for there, like this. Now the next one here, like this. Again, I can click any of them. Let's take this one here, take it up here, somewhere like here. And then I'll switch layers by pressing Control L. I can select what layers I want to go to. And of course, not the isolation layer, because this is not a signal layer. So let's go for layer 2. It will automatically add the VS. And I can route up here. Again, switch layers to layer 1. Automatically the VS will be placed, and I can continue the routing and complete it like this one. So this is basically my circuitry here. If we switch to the 3D presentation here, you can now see that I have, of course, the connectors here. I have all the connections in here. I have the VS, but you can, of course, see if I print something like this, there will, of course, also be a short here, which I don't want. I do want the short here, but not there, of course. So let's actually have let's fix this one up, switching back to 2D mode here. So I will use the tool called Printed Electronic, and I will activate the generate dielectrical patterns for me here. Now the tool then automatically detect shorts like this one here and generate a isolation pattern for it here. You can ask the tool to either generate or remove the patterns. So in this case, I would like to generate it. I have to select the dielectrical layers, which is preset to layer 3 in this case here, and the layers above, layer 1, below is layer 2 here. For the electrical shape or the dielectrical shape here, I can set this one to auto or manually define it myself here. And I can also ask the tool to fill the gaps here. Let's first of all not fill the gaps here, and let's apply this one. So now you can see that the system generated these isolation paths here in layer 3, the isolation layer. If we switch to 3D mode, you can see that it's being represented like this, so there's no short anymore. So this is almost done. Switching back to 2D mode here, I would like to also show you, let's go for the tool again, Printed Electronic, and in here, now I would like to fill the gap here. So let's say that if the gaps is less than 20 mil, it will be filled. So let's see what that looks like. And now you can see that they are entirely filled in here. This makes the printing a little bit easier. So let's go with this one here. And for the final thing I need to do with the design is actually changing the via slightly, because if you look at 3D presentation of it here, I don't actually want the hole in there. There's no need for it actually. So let's go back and change this one. If I select this one, I can ask the tool to select any similar project by right-clicking, say find similar object. The object kind should be a via. If this is the same, it will get selected and I will clear any of my other selections of it. So let's go for that. Okay. And if we look at the properties for all of my vias now, I can change the diameter here. So for instance, let's make it a little bit less, something like 30 mils here. And the hole size should be 0. Then I don't have any holes. Now you can see that all of my vias has been changed. We look at the 3D presentation, you can see it's looking something like this, and there will definitely be a short from layer 1 to layer 3 here, sorry, layer 2. And the isolation of the material is there also. This is basically how to design something like this. Quite simple to generate the patterns because the tool now is supporting this feature for you. So I will save the PCB And I will also save my design to the server here. So it says it has unsaved file. Yes, let's do save them. Let's do this as an initial push. And I will commit this one to the server and make it available to my entire team now. Now, I do, however, have one question for my manager here. I'm a little bit in doubt of this connector here, so I will ask him to verify that this is the right connector here. So I will place a comment on the sheet here. Let's actually pin this one. And I will add place for an area like this and ask are these the right connectors? I will post it. And then I will share my design with my manager, and his email's name is like this. Like this. Now he's not part of Altium, my workspace normally, so I will only give him view access here, and I can add a note. Please correct. Okay, and I will share the design. Now the system will recognize that he is not part of our workspace here, so it will ask me if I want to just share it with him or I will invite him into the workspace. In this case, I will only share it, so it will share this one with him. Now this has been shared and I can see who has access to it. I have access to it since I'm the owner of the design. And the administrators of my workspace also can do the edit here, but this person here can only view it. Okay, so let's have a look at how it looks at my manager's emails. Let's have a look at this one. Let me just quickly log on. Like this. So he will receive an email like this one from Altium 365. And if you click at here, let's say, okay, these are my comments. Please check if connectors are correct. And he can then click here to open this one in Altium 365. When he directed to a sign-in page here, so all he generally needs in order to be able to do this one is that he needs an Altium Live account, and this is like a two-stage security that we built into it. So he will need to sign in, and this is of course free of charge. Like this. So this is the schematic. As he can see it here, he can see the PCB as well. He can see what kind of layers he wants to. He can enable them and disable them. He can also see a 3D presentation of the design here, and he can of course move it around like I can. He can also see the bill of material. In this case, he can click here. You can see where the connectors are set also here. But if we go back to the schematic here and look at the comment for it, it says, are these, if I click here, it will ask me for this area here, are these the right connectors? Okay, let's have a look at the bill of material and click here. Then he can quickly go to Octopart and see who distributes this one, the pricing of them, and of course, data sheet can be downloaded. He can really inspect everything about this connector here. So I think as a manager here, this should be okay. Let's give a comment back here. Let's say yes. Okay, that's this. Let's reply. And if I then go straight back to Altium here, you will see here, if I click here, my manager say, yes, this is okay, please continue the design. Okay, I will do so. Oh, sorry. Thanks. I will reply, and I can actually also resolve this one by clearing this one out of the list here. And in this case, you will still see it, but you can say to show resolve comments on here. Okay, so this is pretty good. We are ready to produce this one. So I kind of like need to create Gerber data for it, for instance. So let's add something to the project again. Let's add a output job file where we can generate Gerber data and everything else. Let's first save the file here. And we will save this as fabrication. And for the outputs, I would like to add some, saying let's add Gerber files. And let's configure this one here. So it's okay to be in inches, and the 2.5 is definitely okay. So let's go for layers. And in this case, I will plot the used one. So it will plot these layers for me. This is okay. I need some place to store this one here. So I don't need the PDF. Let's remove this one. And also not the video. But I need some kind of folder structure to put it. So let's call this Gerber. And make this one the connection here. If I then generate the content, and normally when you generate Gerber data for a normal PCB, you will also need to create drill files, IMSE drill files. But in this case, we don't actually need to drill, so we don't need the files actually, in my opinion at least. I can also add IPC 2581. That is also possible. So let's 581 like this. Or ODB++ files can also be generated. Like this. Let's try and generate the Gerber so that you can see what's it like. You can see I get the Gerber report here. And I also, if we look at what's actually generated here, we can see the Gerber top layer. Where's this one? This one. So this is the Gerber data for the top. And this one here is for the inner layer and for the bottom layer. Right, so my Gerber data are correct. The only thing I need to do now is actually to save my design to the server so it's available to the team here. Yes, I want to save it. I will leave a comment. Gerber data, commit and push. Okay, now everything available to the team, and I can actually, move on to the next project here. And I actually had a request from the mechanical department saying, okay, we need to have a look at the design. So could you please send this for us? So I will actually close all of this one here. And I will open up a project that I already stored on my workspace here. You can of course here see all the projects in here, and if you click this one up here, you can see a short presentation of the project, and you can see that it has one schematic and one PCB. Who was the author of this one? When was it last modified? The folder in where it's stored on the server, and if it's local to me, also where I have it stored here. So let's actually take this project here. So this one. This is the project that I need to send to the mechanicals. So let's open this one. And let's open up the PCB. Like this. And you can see that this is actually coming from TactoTek. So what I need to do here is actually work together with my MCAT guy, department here, and the way to do this is with the MCAD Co-Designer in Altium here. So I'll just enable the panel here, and the only thing I actually have to do is actually push the design. So let's give him a comment, say please check with the enclosure, and just post it. Now Altium will then generate native data for the MCAD file, for the MCAD, and all he has to do is actually use his, let's sign out of this one here. So he will actually just have to activate SolidWorks. Oops, SolidWorks. It takes a few seconds on my computer. So while it's starting, I mentioned that Altium is generating native files, a special place on the workspace so that we can work together with the MCAD tool here. So it's like a cooperation between Altium and SolidWorks. In this case, it also works with Autodesk Inventor, and it works with Creo also. For now, we are looking at more mechanical tools, but for now, this is like this. So this is my SolidWorks here. And in SolidWorks, I have installed an add-on called Altium Co-Designer. Now, this can be downloaded from our web page, and it's free of charge. There's no additional license fee from Altium or from SolidWorks, actually. So I'll just use this add-on here. It will ask me to sign in, so let's do that. Like this. Once I'm signed in to my workspace here, I'll just check that I'm using the right workspace. Yeah, this is okay. I can actually just pull the board from server, and it will say, okay, which board do you want to pull? I would like to pull this one, and just open it. It needs to be saved somewhere, so let's save it here. And then it will check all the designed files, and then in a few seconds it will show me the design. Now, what it also will do is that if there are models in there, in this case there are some LEDs, it will actually also take the 3D models from my workspace. So it's not just a graphical presentation, it is actually a sampling, as you can also see here. So this is the model here. So let's have a look at it. You can see that I have the assembly here. See LEDs here, like LEDs 1 and 2. And if I select one here, let's actually zoom in a little bit here. Use my 3D mouse and try to select this one here. Like this. I'll try to move the component, and let's move it by delta XY. Let's move it 1.5 millimeter and apply this one. You can see that it's now been moved. Of course, this is not the right correct place, but this is just to show you what's possible in Altium actually. So let's accept this one here, and let's push it back to Altium now. I have tested it and I have moved this component. Now I want to push it back to Altium so that I can continue my work there. Let's, you can also see the comment that I gave here. So let's push it back. Like this one, and I will post it. Then it goes back to the workspace server. And in Altium, I can also see this change here. Now I'm in Altium here, and you can see, okay, I got some information said, okay, he moved the LED once. If I want to view the changes here, it will come up and detect them. It will say LED 1 here has been moved. So if I just zoom in, you should be able to see it here. You can see that it's physically moving this one to there. And then I can say, okay, this is okay for me. I will apply this change. And the LED has now been moved. And I can clear up the routing and, save the design. And that's basically it. Okay, this is what I wanted to show you, how Altium can work with this IMSE, and how we easily work with the cloud solution, making sure that everybody in the team have these design changes. So I will stop sharing screen and send it back to you, Tuomas.
Great. So thank you, Sten. As you saw, Altium Designer has many features for supporting IMSE electronics design directly, but in addition, how to do the co-design between electronics and, for example, mechanics. So now we have a couple of minutes for questions, and before that, we would like to ask one question from you. So there is one question coming in the, yeah, actually we see it already. So what would you like to learn next? And please answer those questions. So based on this, we are planning our coming webinars. And meanwhile, I will check what kind of questions we have. So there is one question relating the geometry or form of the structural design. Of course, there are constraints, so we cannot do everything. But for example, 90-degree corners are impossible. So because of the materials cannot stretch so much. So very sharp, very deep formings are difficult, and those sets certain constraints. But those, when we have this kind of products in our table, it typically means that we do close collaboration between electronics and mechanics and try to find out optimal solution from mechanical point of view, so that we can fulfill the customer requirements. For example, we can do some features on the backside of the part which are not visible in the A surface. And then about materials of molding. So unfortunately, I'm not specialist in this area, but what I can say that basically we are using standard off-the-shelf materials. If you would like to get more detailed answers, so please contact, for example, in the sales at TactoTek.com, what you can see in this slide. Then about components, surface mount components that aren't compatible with injection molding. So yeah, for example, high integrated circuits with very fine pitch, those are challenging in terms of not only injection molding, but also for the printing, maybe difficulties for this kind of component. So typically what we are in molding are LEDs, passive components. And this is because main reason is that it's in many cases it doesn't make sense to put everything inside the plastic, but just the features what we need to have inside. And yeah, and unfortunately we don't have any more time for questions, so time is up. If you have any questions, any other questions, please contact sales@tactotech.com. So from there you will get the answers. But that's all from today's webinar, Designing Structural Electronics. So thank you all for joining and have a nice day.
Yeah, bye bye all.